The title is Rotational Properties of Multispecies Bose Gases in the Lowest Landau Level.
Thanks. And well, like all the others, I also would like to say a big thank you to Chris and Nigel for inviting me. And of course, coming from Scandinavia, thank you so much for the nice weather. So I realized preparing this talk and knowing I was going to speak to two communities, I'm probably going to insult everybody here at least once by saying some very, very basic things, so please bear with me, but I'll try to make it self-contained. So I'll start by recapping a by now rather old story of rotating bosons in the lowest Landau level and how it connects to quantum Hall physics. And after that introduction, tell you a little about two and also tiny little bit about three species, Bose gases. And some of this was already mentioned by Janendra yesterday, so maybe I'll cut some corners there. And in particular, I'll show you some some results and funny puzzles that came out when we tried to play with applying the composite fermion formalism to these systems. And just a few words of conclusion at the end. So, historical recap. I always get shocked when I see this line because it's actually over 20 years since the first breakthrough of atomic Bose condensates, and it doesn't feel that long ago. But pretty quickly after that, people started to get interested in rotational properties. And so I remember still when the first quantized vortex was reported by two groups. And then things evolved quickly. So by 2004, there were these beautiful vortex lattices of hundreds of vortices. And oh, I'm sorry, my credit line vanished. I think this is Eric Cornell's picture. Yes, yes. I did ask you for permission at some point. But no, there was a line of text, and when I shrank the figure, it just somehow went into alien fonts, whatever. And what was discussed at the time was the qualitative picture that as you keep increasing rotation, your cloud would go more and more pancake or disc-shaped and more dilute, which means weaker interaction, and at some point one would reach the lowest Landau level. And I'll say a few more words about this on the next slide if you happen to not have seen that connection. And then the next theoretical prediction was that at some point there will be a transition where the system enters a new regime where instead of vortex lattices like this, one enters a regime where you can have strongly correlated states of the quantum Hall type. And of course, as has been mentioned already, rotation is sort of the original and conceptually simplest way of faking a magnetic field in these systems. There's been a long development later on when people realized that rotation of a pure harmonic trap for practical reasons wouldn't be the way to go. There's many other ways of producing synthetic magnetic fields nowadays. Although, as we heard yesterday in Nate Gemelke's talk, as far as I'm aware, the only experimental realization of probably a atomic Bose gas in the quantum Hall regime was actually obtained by a version which involves rotation. So very quickly, and most of you have probably seen this, so I'll be talking about wave functions, and there's been quite a lot about trial wave functions already, but sort of for the people not from the quantum Hall community where this comes from. So of course, the historical background is the quantum Hall effect, which is a 2D electron gas and a strong magnetic field, which means it's often assumed that the physics takes place in the lowest Landau level. Now, I don't have to explain these figures to you after all the introductions yesterday, but the main point I want to make here is that if you assume you're in the lowest Landau level and you want to look at states with a good angular momentum, then you write down the single particle basis states of this form where commonly one uses these complex coordinates. And, well, you can forget about the normalization constant and the Gaussian factor is always there and it's always suppressed, but the point being that a single particle state with angular momentum can be written as z to the L. And so any generic, whatever it may be, many-body wave function you may want to write down is then a polynomial in n coordinates, as many as the number of particles. It has to be fully antisymmetric, and the total angular momentum has to equal the degree of the polynomial. And, well, this is the insulting part, of course. To many of you, this is extremely basic. And it's maybe a funny thing seen from the outside, but in quantum Hall physics, there's this long success story of qualified guessing of many-body wave functions, if you like. Well, very qualified, but with a number of schemes, which of course started with Laughlin's famous wave function, and which was later extended by various hierarchy schemes. And I'm highlighting composite fermions because I'll get back to that, which have proven very successful, not in the sense that they are exact. I mean, certainly for Coulomb interactions, they're not exact, but because they are believed or have been shown to capture the essential properties, such as the correct fractional quantum numbers of fractional excitations, etc. And I'll be talking about trial wave functions of this type for bosonic systems. So in case you haven't seen this, the mathematical equivalence between having a rotating system and a magnetic field, basically, so the basic step comes down to being able to complete a square. Because if you just look at the one-body Hamiltonian for a 2D harmonic oscillator, if you add and subtract the pertinent cross terms, which are these, so LZ, then you can write this as a complete square plus this other term, and then, well, there's other ingredients. You put it in a rotating frame, and you go close to the limit where this omega is cancelled by the external rotation, etc. But the essential thing is that because you can write it like this, it looks like the Hamiltonian of particles in an electromagnetic field. And that's why people talk about these bosons then being in Landau levels. And in particular, if you go to a regime where the interaction is sufficiently weak so it doesn't mix the various Landau bands, then one can look at the lowest Landau band separately. And that's the regime we'll be talking about. So then obviously if you look at a non-interacting system, you have this enormous degeneracy, which is essentially the number of ways your total number of angular momentum quarta can be distributed over the number of particles. And there's a combinatorial formula for it, but it explodes very quickly. And so then if you add interaction, obviously that will lift the degeneracy and select the lowest state. And some 15 years ago, the term Erast state entered the field. That's due to, as far as I know, Ben Mottelson, who I should mention, he turned 90 this Saturday, so I wanted to mention him. And he's still going strong, and he's still interested in these systems. But it's a term from nuclear physics, and it's a Swedish word. It means the most dizzy state. So, and as I remember the story, at some point Ben bumped into Chris Pethick in the corridor, and Chris was looking into rotational systems, and Ben asked, so what's the Erast state of a Bose condensate? And so somehow that's how this term came into the field. So here's an old picture just to illustrate. So this is just an exact diagonalization of 4 bosons with a contact interaction. So this line, it's as a function of total angular momentum, and this line connecting all the ground states, then that's what people refer to as the Erast line, thanks to Ben Mottelson. So in accordance with what I said 2 slides ago, you can then imagine writing down some generic many-body state, which then would have to be symmetric because these are bosons, but otherwise in total analogy to the quantum Hall picture. And people thought of this already long ago, and the first people to look into this, of course, were Nigel and collaborators, Nicola Wilkin and others, noting that there might be a Laughlin state and then extending to applying the composite fermion scheme to study the properties of some of these states. We've been picking up on various aspects of this on and off through the years. But one sort of funny thing that came out of it already at the beginning is that you sort of, I mean, I wish I had a chalkboard, but as was already discussed, somehow the idea or one argument of validity for using the non-interacting composite fermion approximation is that you attach these flux quanta or correlation holes or vortices, whatever you like to call them, and they build in good correlations so that, you know, even in assuming they're non-interacting, you get a good approximation. Now, if you sort of naively just pull this construction all the way down to the lowest angular momenta, technically a Jastrow factor has an angular momentum order n squared, and you want to pull it down to the lowest angular momenta, it means that the Slater determinant has to subtract angular momenta after projection. It means you act on your Jastrow factor with a whole lot of derivatives to take away almost all the powers of the original Jastrow factors. And so in a sense, you might think you've taken away all the good correlations. Why should this work? And it turns out it works all the way down. So for instance, for L equals n, the composite fermion trial state, in fact, becomes exact in the thermodynamic limit, which was sort of a funny observation, and I'll pick up on some of that later on. So up to now is a really old story, and more recently people have looked into multispecies systems, and in particular, as Janendra discussed, two-species systems. And as far as I'm aware, there are several ways of realizing them in experiment: two types of atoms, two isotopes of the same atoms, or two different internal states. And of course, this promises much richer physics because you have some new parameters you can vary, like, the two types of interaction or the masses and the particle numbers. So people have studied many of these aspects and mapped out phase diagrams, miscible to immiscible phase transitions, what kind of vortex lattices you might get, etc. It's not the focus of my talk. And also, again, referring back to Janendra, what is often assumed, and I think it can be approximately realized in experiment, is that the inter and intraspecies interactions are the same, which I will refer to as homogeneous interaction. So then you can borrow much of the formalism from a spin 1/2 system. So it's like a pseudo-spin 1/2. And also, of course, you can have bosons with a real spin equal to 1, which would then, in the same manner of speaking, be a 3-species systems. And people are interested in that too. So I'll mention that briefly also. So the next slide I can skip over pretty fast because that's exactly the things Janendra reviewed yesterday. There have been studies in the quantum Hall regime, and in particular, there's this discussion whether or not the nu equals 4/3 states might be a non-abelian spin singlet state, which is this state which was proposed by Karel-Jan Schoutens and Eddie Ardon a number of years ago. And I was going to ask Janendra if this has been settled, but apparently it has not. But there is a competition between this and composite fermion state, and so I guess it's unclear. And then also, as was mentioned yesterday, people study integer bosonic quantum Hall states because there may be some of these symmetry-protected topological states that might actually be realized in this context. So I'm not going to say more about that and move on to some of the stuff we've been interested in lately. So the work I'll talk about is with students of mine, Marius Meyer, Olalia Bötre, master student, Vidar Skogvold, and Srijit, who is a postdoc and was anodita at the time. So we look at two species Bose gases in the lowest Landau level. We assume homogeneous contact interaction. And one motivation for sort of getting back to this after some years was a paper by Thomas Papenbrock, George Kavulakis, and Steffi Reimann, which identified a number of analytically exact many-body states in the spectrum of these systems at low angular momenta, so up to M, where M is the number of particles in the majority species. And first of all, it's kind of rare in physics to find analytically exact solutions, although of course it helps that these are contact interactions and not Coulomb interactions, I guess. But so these were some, but not all, of the states in the low energy many-body spectrum of this system. And so we asked ourselves several questions. Can we, first of all, understand these states in a different manner? Can we find some of the others? And also, given the somewhat surprising success of the composite fermion technique for the one-species system, can we try to apply them to this system, and will it again work? So just as for one species, that was not a priori obvious, and so we set out to play with this. And as Janandra introduced yesterday, the sort of generic form of a composite fermion Trolley wave function for two species, or spin 1/2, is then this form, where the phi's are the Slater determinants for the up and down species, and J is a Jastrow factor. And since we're assuming homogeneous interaction, it means that it's just that the Jastrow factor is blind to the spin species, so it's just a Zi minus Zj containing all the coordinates. And when we did this, we stumbled across another kind of puzzling thing. So it turns out, I mean, when you write down these Slater determinants, you have certain guidelines. You want to fix your total angular momentum, your pseudospin, etc. It turns out this does not, in general, uniquely determine what the form of these Slater determinants should be before projection. And in particular, it turns out that two very different looking pairs of Slater determinant after you perform the projection, because somehow the derivatives conspire to cancel terms, end up giving you the exact same polynomial, or you may end up having linearly dependent ones. And that is something which is particularly pronounced in this low angular momentum regime, although it has also been seen in the actual quantum Hall regime. So let me give you a simple example. L equals angular momentum equals number of species A equals number of species B. That state can be constructed. I should say we're doing all of this in the disk geometry, so we're thinking small systems and disk geometry, and that's where we find these exact identities. In that case,
sorry.
Yeah?
I'm a little confused there. I thought L referred to the Haldane sphere. So could you say this is a disk geometry?
Yeah, sorry, I should have said that right away. It's disk geometry, and L is the degree of your polynomial. So you have a rotational, I mean, like a circular droplet you can think of. So L is the total angular momentum in your droplet.
Degree of the total angular momentum or the maximum angular momentum of a particular?
No, the total angular momentum of a given state you want to look at.
Adding all of them.
Yes.
So what is M then?
Sorry?
So what is M?
Oh, that may be a clumsy notation. N is the number of particles in the one species, and M is the other species. So, yes, now that was...
But usually you wind up with L, the minimum L is of order n squared, isn't it?
Yes, and that's exactly the point of this figure, because the Jastrow factor is of order n squared, and to get down, which may look artificial but turns out to work really well for some reason, to these lowest angular momenta, you have to take away most of it, which also means taking away most of the good correlations sitting in the Jastrow factor to begin with. So if you think of this as the lambda level sketch the way it's normally done, this is the lowest lambda level and angular momentum going to the right. You actually occupy states with negative angular momentum in the lambda levels, which after projection translates to acting with, in this case, Slater determinants of derivatives. So they would be z bars before projection. So that you get down from this order n squared to order n. And so that's the point of this figure. And that's...
What's
yes?
little n?
So in this case, n is 3. That's the number of species 1 particles. So this
little n.
Where's
So
which?
why wouldn't the low
Yeah,
have
so-
more degeneracy than the? I mean, why?
Oh, they continue to the right here,
Okay,
right?
I
But
see.
every lambda level starts at m angular momentum minus n. So that's, I mean, in the disk geometry. So this would be lowest lambda level angular momentum 0. This is third lambda level angular momentum minus 2, etc., etc. And since you have two species, this is the first Slater, this is the second Slater. So after translation, so the single particle states going up along this diagonal, they're just z bar to the power n, which translates to these derivatives. Yeah, I'm sorry, too many details I didn't explain. But I wanted to include this as an example because, first of all, it's what I will later refer to as a simple state, which means there's never more than one composite fermion per lambda level, which is like the extreme opposite of what you're used to for, you know, the Jane sequence where you actually fill lambda levels. So this is, in a sense, a very different regime. It is also what I will later discuss, so I want to point out already, a highest weight state, the way you can define it in the disk geometry. And what is kind of cute, it's the exact ground state, not just for 3 + 3 particles, but you can continue filling up every second going up here, which is just one example that, although it may look artificial to use the composite fermion construction in this regime, it actually gives you good states, and in this case, even the exact.
When you say it's exact, is it just because you have a node on every interparticle separation? And there's
No, you no longer have that because you've differentiated away most of them. I mean, you start with this thing which, as Bert was saying, is order n squared, and you act with so many derivatives that only n is left. And of course, in big systems, n is much smaller than n squared. So the nodes they're long gone. So in a sense, it's not, that intuition no longer works. So so I don't have any good intuition for it.
The ground, what's the size? It occupies everything is very compact or spread out in this.
It is.
Everything is, the bosons are all piled up.
They're
one
pretty
above the other.
compact because, I mean, the L = 0 state, they all sit on top of each other. And then you've excited order 1 angular momentum quanta per particle. So it's much more compact than,
And
say, a
it's
Laughlin
ground
state.
in which with only,
Just delta function interaction.
but it's in terms of pseudo potentials, you're only.
It's like, yeah,
taking
S wave.
The V equals, the L equals 0.
Yes.
Different from 0 and everything
Yes.
else is.
Yeah. So we're staying in that simplest limit. Yeah. So a few more words about how you select these later determinants. So this is getting a bit technical, but one thing is we're looking at translation invariant states, which in this formalism translates to making compact states. The reason being that any center of mass excitation can sort of be trivially tagged on afterwards. So normally one looks at translation invariant states, which means filling these lambda levels compactly to the left. Now, when I say highest weight in this context, I mean maximally aligned pseudospin, where the pseudospin up and down is the two species. So, and that can be implemented, as one may look up in Janendra's book, by making sure these Slater determinants obey something called Fock cyclic condition, which means that every state occupied in the Slater of the minority species also has to be occupied in the majority species. And then you want to fix the total angular momentum of your states. You want to look at one certain place in your certain angular momenta in your Eurist spectrum. And that gives you restrictions, so you can't just write down any Slater. But they don't fix these Slater determinants uniquely. And sometimes, that's just because there are different states obeying all these criteria. But it also turns out that writing down these Slater determinants, many times you find that after doing all this cumbersome projection and acting with these derivatives, you end up getting identical or linearly dependent final polynomials. So in some miraculous cancellations, these derivatives somehow conspire to cancel terms so that you get linear dependencies or identical results at the end. And as you saw already, so what kind of characterizes this regime is that the Slater determinants actually mainly consist of derivatives, which is very different from what I would refer to the quantum Hall regime, where you have states of order n squared, angular momentum of order n squared with filled lambda levels. So here's an example of the point I'm going to make. This is a table for 2 plus 6 particles, angular momentum in the first row here. Next row is the actual number of linearly independent basis states. The next row is the number of linearly independent composite fermion basis states you can find. And one thing you may want to remember for the next slide is that up until 6, which is the number of particles, or below 6, the number of particles in the majority species, these two numbers are the same. However, the final row is the number of different pairs of Slater determinants, having all the correct quantum numbers before projection. So, so for instance, in this case here, you have 20 different looking pairs of Slater determinants with different occupation patterns in these lambda levels. And if you're patient enough and you do the projection, you do all these derivatives, they all end up being the same polynomial. And that's, of course, a hassle if you want to do numerics. So you can do several things with this. First of all, you can do what is called the full composite fermion diagonalization. You do the work and you find all your basis states, you project, etc., and then you diagonalize the interaction in the space spanned by all these compact highest weight candidate states. And the first thing you observe is you exactly reproduce all the states found analytically by Papenbrock et al. For L smaller than the number of particles in the majority species. And as you go beyond this point, they are no longer the exact eigenstates, but very good approximations. Now, this is not as impressive as it sounds if I just say it like this, because if you remember back to the table on the previous slide, in this regime, the composite fermion construction gave you as many linearly independent states as the actual size of your bases. So in this regime, all we do is writing our bases in a different and more convenient form because they're really equivalent. But the neat thing about using the composite fermion one is you already have translation invariance and highest weight state, etc., built in. But other than that, you're spanning the same space, so obviously you're going to get the same states as from exact diagonalization. Whereas here, you have slightly fewer basis states, and it's no longer exact. But given the fact that, like I showed you, for instance, you can have like 20 a priori different looking states which reduce to the same final polynomial, it's very computationally demanding, and then you may ask yourself, why on earth would you do this in the first place? You might as well do an exact diagonalization. So that's one of the issues we try to address. And one observation is if you reduce, you can reduce the number of basis states without losing very much by identifying a subset of these composite fermion candidates whose contribution turns out to stand for most of the good overlap. So the others aren't really that important. And it's a natural thing to do because it turns out that this subsets corresponds to, if you naively think that minimizing the cyclotron energy of the particles in the composite fermion lambda levels somehow translates to lowering the energy of the real state. So it turns out if you construct them such that there's no more than one composite fermion per lambda level that is equivalent to minimizing the composite fermion cyclotron energy, and you only use those states, you still get extremely good overlaps, and you reduce the problem by quite a lot. So that's a simplification. So here's an example, 4 plus 4 particles, and all the blue dots are from an exact diagonalization. This is only translation invariant states. And the different colors here, the resolution, of course, is awful, but the different colors denote different pseudospin. And the way this has been constructed is really, this is really putting together many spectra. You start from 8+0 particles, and you find the highest weight states, and then you know, because of the pseudospin symmetry, that a state of the same energy will also be present at 7+1, 6+2, etc., and 4+4 states. So, you know, taken together, this gives you a pretty good approximation to the lower part of the spectrum with these. So it still, many of these are in fact exact, and some of these have very good overlaps. So that's what we refer to as the simple states I mentioned earlier. However,
5 minutes.
yeah, I think I'll be roughly done by then. But then there's this puzzle, this kind of annoying thing with the linear dependencies. So like I said, it looks like before projection as if the number of different composite fermion candidates is a lot larger than it actually is, because after you do the projection you find many of them are identical or not linearly independent. And even after the restriction to these so-called simple states, that is still the case. Things get better, but it's still a problem. And it's not just, it doesn't only show up here. So we discussed this with Janandra, who also discussed a similar problem in the context of fractional quantum Hall states for fermions in higher bands. And I remember this formulation from your paper, that there must be some as yet not yet understood mathematical structures in the composite fermion formalism, and I think that's roughly where we stand, really. So we, or well, actually mainly these two PhD students, they set out on this combinatoric tour de force to try to understand this, at least in the context of simple states. And the wish, of course, being, if you want to use this for numerics, to somehow be able to spot from the form of the Slater determinants which ones of these are, you know, to reduce that to a basis of linearly independent states before doing the projection and just staring at your polynomial, because that's really the heavy part of the numerics. So, well, it's a very technical manuscript, so I'll just mention a few ingredients. First of all, that in order to even be able to handle these, they came up with a very convenient letter string notation coding whether or not at a given lambda level both species or only one or only the other or neither is occupied, and translated this to this sort of letter string code. And there's various ingredients in their proof. One is to exploit translational invariance, which means if you're looking at a state psi at some angular momentum, this state being translationally invariant means you can act on it with this operator and get 0. And this, of course, will give you linear relations between states at one angular momentum less. They found a number of identities for certain ways of permuting these occupation patterns. Combining the above gives you even more identities. They find a certain kind of mirror symmetry in how you can change these occupation patterns without changing the outcome. And there is also a generalized version of this referred to as generalized translation invariance, which goes into the proof. And they kept going for months, and they ended up with an algorithm that you can apply to a given pair of Slater determinants, and before projection identify all the linear dependencies, not just for simple states. They moved on to general compact states covering the Erast line for two species all the way down to the 2-to-1 Halperin state, and also for single species bosons, and to some extent some of this carries over to fermions. So they kind of reached the goal, and the paper has been with referees for 7 months now, and I think somebody is very much stuck in the combinatorics. I have no idea what's going on, but so we don't know what comes out of it. But this is, you know, analytical proofs and tested numerically, so we believe in it. But of course, if you're working in this business, that's very annoying, because you kind of think there must be a simple way of seeing this. Right? There must be some way of understanding it without doing 20 pages of combinatorics, and we don't. And I'm not sure it's possible, because after all, these were pretty complicated things. but that's one thing one would wish to do. Another thing my student has started looking into is to go away from this idealized limit of homogeneous interaction and still see what you can do in terms of trial wave functions there. Physically, of course, this is the regime basically where the first vortex enters the system. So it's not at all the quantum Hall regime. It's more like the single vortex regime. So you can use these wave functions to study that. Then there's the idea Janandra told us about yesterday, to use two species systems by just having one or two particles from a minority species to probe anionic quasiparticles. So that's something people are interested in. And of course, one thing that's fascinating about this particular regime, it's exactly the regime where Nate Gemelke is doing his experiments, except that's for a single species. So one might hope to that those experiments will be able to address two species systems also. So so we're in exactly that regime. When I talked about these things at a workshop in Dublin, Carl Jan Schoutens approached me and said that he and Nick Reed and some others had written a paper many years ago, stumbling across some identities for the Earth spectra of spin 1 bosons, so 3 species. And he asked us if any of these could be reproduced doing what we're doing. So I have a master student looking into that right now. And so far, the answer is yes, for whatever he's been able to look at. And the last thing is I'll end with a commercial spot. Next August, together with Eddie Ardon and Jonas Larsson and Marcus Henrich, I'm organizing a 3-week workshop at Nordita in Stockholm entitled Topological Phases in Cold Atom Systems, which is kind of the same topic as here. So we haven't started sending out emails and making web pages, but I hope to see many of you there. So I'll stop there. Thanks.
And one of the interesting things about spinor condensates is things like phase separation and so on, because of the differences in the scattering lengths. Did I understand you have not allowed the scattering lengths to be different?
Yes, we have not at this point. That comes into, when I say go beyond homogeneous interaction, that's exactly that. So we just last week we started talking about it, so there's no results yet, but that's certainly one. So people, much of the literature I've seen, at least on rotating systems, is in this ideal limit, but certainly we want to go away from that.
Short question. So are you looking mostly for the angular momentum regime where L is comparable to the number of particles?
Yes.
So in those cases, then I would have thought that the ground state would be a vortex lattice state typically, and then but again, I think it's somewhat similar to the previous talk that if you do your calculation in a basis where you conserve angular momentum, then you would not be able to review the condensate. And then I think if you put in any tiny little bit of the symmetry breaking field, and then then the whole thing would instantly resemble. I mean, you can look at the ground state wave function.
Yes.
Then that I believe would resemble into a condensed state. I think another way to review it is just to compute the single particle density matrix.
Absolutely.
Right? Yeah.
Yes, I didn't include that here. My student has been doing that. But actually for the very lowest angular momenta, it's not a vortex lattice. It's the regime where like the first vortex starts to come into the system. Whereas, you can pull it all the way down to the point where the interaction energy goes to 0, which would be a Laughlin state in the single species system and a 2-to-1 Halperin state in the two species system. And along that way, obviously, you start to make a vortex lattice. And exactly like you say, it's if you have to break the symmetry numerically to see those. But yes.
So, you mentioned this paper of ours where we found that we can also identify the linearly independent states by eliminating certain composite fermion excitons. So just wondering if there is a connection or whether you have looked at how these rules apply to the spherical geometry.
We talked about it. We haven't really gone into detail. And there's another important difference, which is that you're looking at fermions. And many, not all, but many of these identities and the proof that we've been looking at, they are simple and exact because you're only differentiating on a single Jastrow factor, as it turns out. So we talked about it, we tried a bit, but it's not entirely trivial to translate to your work.
Okay, let's thank Susanne once again.